Next educational video. Let's study a very important type of vector fields known as conservative fields. A vector field F, capital letter F in bold, is said to be conservative if it can be written as the gradient vector of some scalar function f, small letter f. Let's recall the meaning of gradient vector. For the case of two-dimensional fields, delta f is a vector whose components are the first order derivatives. So in this case it will be df dx for I and df dy for j. If we are in the three-dimensional fields, then we have one more component df dz. Let's learn a jargon. In this case, little f has a name. It's called a potential function for g. A quick remark, an obvious one. If little f is a potential function for g, then little f plus any constant c is a potential function. And this is obvious because when you differentiate c with respect to any of the variables, you get 0. So potential functions are not unique. Conservative fields are not uncommon. Here's a quick example of a conservative field that we all know. We must have learned this in elementary physics. The gravitational field. You take two objects of masses m1, m2 respectively. There will be a force acting on each of them. According to Newton's law, the force has a formula given by this expression. m1, m2 are the masses. Capital G is known as the gravitational constant. And x will be the vector, the position vector of one of the masses. In this setting, the mass m1 is positioned at the origin. And we are looking at the force acting on the mass m2. It's well known that gravitational fields are conservative. And the potential function f has this expression. I leave it to you to verify this. All you have to do is to differentiate little f with respect to x, y, and z to get the first, second, and third components of capital letter F. One natural question to ask is this. If we know that a vector field is conservative, how do we find the potential functions? So this example will show you the techniques of doing so. Obviously, we use the definition of a conservative field. We write the given vector field in the form of the partial derivative of the unknown scalar function f that we are trying to find. We will then be able to form two equations. Comparing the first component, we will form equation 1. And comparing the second component, we can form equation 2. What should we do next? Keeping in mind that our job is to find little f, we will start with equation 1 and try to get little f from equation 1 by doing an integration. That is something obvious because we are given a derivative, df dx. To get a function from its derivative, we have to perform an integration. So let's integrate equation 1 with respect to x because we have df dx. So we end up integrating y cubed minus 6xy with respect to x. We have done partial integration before under multiple integrals. When doing this integration, we will keep y as a constant. So as a result, y cubed will become y cubed x because y cubed is like a constant. Similarly, 6xy will become 6y, the constant, times the integration of x, which is x squared over 2. Finally, we add an arbitrary constant. A word of caution, we usually write a constant term, say a, for integration constant. But here we are doing partial integration with respect to x in the presence of y. So the arbitrary constant must be written as a function of y rather than just a constant. So please keep this in mind. So far what we have obtained is an expression for f in terms of x y and the unknown function ay. Or in this case, we should call it a constant because y is now a constant. So we are not done yet. We have to find a of y. And obviously, we will use equation 2 that we formed earlier. The function f that we have just found involving a will be plugged into the expression involving df dy. So that's exactly what we are doing now. We differentiate what we have found in terms of a with respect to y, partially. So because we are doing partial differentiation with respect to y, we will keep x as a constant. And we end up with this equation. And now we do the obvious. Comparing the left with the right, we find a prime y equals to minus 4y. So a will be the integration of minus 4y with respect to y. That will give us minus 2y squared plus some constant b. And substituting this expression for ay into the expression for f, we get the function f in terms of an arbitrary constant b as expected. So you can choose any value of b to get any potential function f.